All right.
Okay, I'll start over. Good morning. I'm going to be presenting our group's project on the comparison of storage mediums and pump storage hydroelectric generation. My name is Brandon Poole. My undergraduate assistants on the project were Ben Beauchamp, Tyler Bishop, and Garrett Bodie. So I'm going to preface this with, I put this together before we covered pump storage hydros, so some of this is redundant. I'm going to kind of move through it a little quickly. We're all familiar with how pump storage hydro works. I do want to point out that it accounts for about 99% of the planet's electrical grid storage. So two modes of operation: generating, pumping. For generating, typically, in the Southeast where we don't have a ton of renewables, it's scheduled when demand's at its highest to augment, what we have dispatched. I do want to point out, like, one of the big upsides to pump storage is that rapid dispatch time. Relative to like a combined cycle plant. If we were shut down, I work at a combined cycle plant. If we were shut down cold, it would take us several hours to come up. So when we're talking on a scale of minutes, these pump storage hydro sites, that's pretty quick, and they offer a lot of flexibility. So pumping, the lower reservoir to the upper reservoir here. In the Southeast, again, kind of, this is scheduled when demand's at its lowest. If we had a lot of renewables, it would be used to flatten that out a little bit more. But the biggest advantage is preventing curtailment. Like a combined cycle site, we don't like to be shut down ever. We don't have to, just because of cyclical stress on all the equipment. Because they're never going to shut down nuclear. But if we can pull 800 megawatts. If we can put an additional 800 megawatts of load on the grid, that leaves us a lot of room to operate. Here's the this is pretty much straight out of the book, the energy storage equation. I did change it a little bit just to make it a little bit easier to read. But energy storage in kilowatt hours, density of water, gravitational acceleration, the volume of water available for use. That's not how much is in the upper reservoir. That's how much you can drain it down. So there's a little bit of a difference there. And then times the average difference in elevation between the upper and lower reservoirs. So this is pretty close to what we actually have at one of our generation sites. We have about 1.1 times 10 to the 7th cubic meters available to generate at an elevation of 198 meters. That's about 5,900 megawatt hours of storage. And I think it's pretty average for a pump storage site, but to put it in some kind of comparison here, that's about 5 times the storage capacity of the largest grid scale battery energy storage system. That might be a little outdated, but I think it's still relevant. That pump storage hydro provides a lot of grid storage. The biggest drawbacks, aside from the cost, which I'm not going to get into, the large elevation change in a relatively small area, being able to hold a large amount of water and something near load centers, right? So that makes it tough to spot these things. Traditionally, all we could ever do was, increase the height that we store, the height difference between the upper and lower reservoirs if we could, or put more water to store in there. There's a company based out of the UK, Reenergize, that's in development of alternative that's 2.5 times more dense. They don't have a lot of information on the fluid dynamics or the thermodynamic properties of it. So for the purposes of this project, I assume they were the same as water, but I think that's going to be a big hurdle to overcome going forward. So if we assume the same volume of storage, we could put that same 5,900 megawatt hour storage facility at a location of 259 feet, which is, I think, turning it into like a small hill, or maybe a large hill. That's like 400 feet of difference. That's going to open up a lot of new pump storage sites. It should also decrease the cost. By how much, I think it's definitely worth investigating, but presumably these things will be smaller than what we have now. Alternatively, if we retrofit, so this is Rocky Mountain Pump Storage Facility. This is one of ours. We have the upper reservoir here, or upper reservoir over here. This is a lake down here. If we were to replace the storage, right? So if we had a closed containment on both ends, a closed system, we replace it with this 2.5 times more dense fluid, we take it from 5,900 megawatt hours to 119 gigawatt. So it's going to be a significant increase. What I wanted to do is model it to see how the turbine generator governor would respond if we increase that, that fluid density. So here we've got a PSCAD model. It's a 120 MVA governor with a hydro turbine, hydro governor, exciter. In order to simulate that increased fluid density, I put a gain of 2.5 times on the torque output of the turbine to the generator. So there was one other thing, the initializing torque value here that had to be adjusted. This was just at the start, just to keep the machine stable when it transitioned to a real machine. But that's at 0.4 right there, but it's only for initialization. The PNID controls for this is the governor model with a PNID controller. I tried using some of the, because we have a similar controller for one of our sites, and I tried, plugging some of those variables in. That did not work. These were more or less trial and error, just kind of understanding what the changes are going to make, and then tuning it down to where it worked. The PNID governor seemed to do the best. Here's the turbine model. One thing I wish I could adjust was the initial operating head. It limits it 2 per unit. Ideally, that would match the that gain of 2.5 times, just so the system, just for better stability coming out into a real machine. Let's see. So here's the steady state results. So the left side here is water, so it's with a gain of 1. And the right is the gain of 2.5. I've got 2 slides for this, so let's see. I mean, everything looks pretty much identical across the board. Here you do see a little bit, so this is the next slide down with terminal voltage, current, and torque. You do see a little bit of a difference, and I should have made this bigger, but down here mechanical torque and terminal current, you see a little bit of a dip where it's not on the other side, and a little bump here. I think that's because of that difference between the initial operating head and the torque input to the generator, but definitely not enough to throw it into any kind of instability range. Otherwise, it looks like they're pretty much trending the same way. So what I wanted to do was test the governor response. So I introduced a 0.3 hertz step change into the governor. That's what I've seen used when we do governor testing for NERC Mod 27. So at 10 seconds, introduce a 0.3 hertz step change, and this is the response. So we get a little bump in real power, drop in reactive power, drop in current, which makes sense, terminal voltage. Generator frequency, so we were coming up to 60.3, which it does steady out on. I think this system response is a little slow based on like the other step response tests I've seen done for real generators. The problem was the mechanical torque spiked so hard with that gain on there. I was trying to limit that to something more reasonable. I don't have like a point where, equipment failure or design limitations or whatever, but I try to keep it within reason. And I think as a result, my frequency response was a little slow. I think somebody who specializes in governor tuning probably get this down a little bit better, but that's what we got. I want to compare the flow rate. So the top graph here is turbine flow rate with fluid density equal to 1, it's water. So we're about 0.52. The bottom is with that more dense 2.5 times gain on there. So you can see that the turbine flow rate, and I should have mentioned before, this is all operating at 84 MVA. So both cases the same output from the generator, but the flow rate is dropped from 0.52 to 0.14. So kind of wrap up, as renewables kind of expand onto the grid, energy storage has got to keep pace. I don't think battery storage right now is there. I think it's like a generation away maybe. With this high density fluid, we're going to have we'd have a lot more locations to use pump storage hydro at. And it may be something we can actually retrofit onto some sites. We have so many, it's 99% right now of the electrical grid storage. Based on this proof of concept, you should be able to work with the existing equipment. I think it's going to turn into a mechanical civil concern more than anything. Especially, when you start talking about the storage vessels and stuff like that. you have to create these closed containers so you don't losses through evaporation and everything else. So so yeah, that's pretty much all I got. Does anybody have any questions? Hello, can you guys hear me?
Any question, guys?
Yeah, in terms of this, I know you said you didn't have a lot of information about the more dense fluid, but do you know if there's any environmental concerns, or how do you contain something for such a large area of pump storage?
So they claim that it's environmentally inert. Whether that's a sales pitch or not, I don't know. And the only way I could see really containing it would just be like just large storage tanks, probably banks of them. You wouldn't want it in like a single large container, probably with banks of tanks. So if you had a failure on one, you wouldn't fail the whole thing.
Okay, because yeah, it seems like you wouldn't want it like in an open pool, because aside from the environmental concerns, it could be contaminated with whatever that could get in there.
Yeah, rainwater or evaporative losses. Like, yeah, there's a lot of things that can go wrong with that part of it. So definitely a closed container.
Okay, thanks.
Yeah.
Any other comments? So Brendan, tell me about your company. How much hydro potential that you have? Is there any plan to expand, or is there any plan to build a pump storage hydro?
So I work for Oglethorpe Power Corporation. It's I think it's the largest utility in the state of Georgia. Maybe Georgia Power is more. We definitely cover more area. We handle all the electrical membership co-ops. So we provide power to them. We provide power to the customers. As far as pump storage hydro goes, we have one Rocky Mountain. It's about 800 megawatts with, like I said, around 5,900 megawatt hours. Right now, I don't think there are any plans to expand that. But I think it's more of a fact, an issue of just location. We got a lot of Rockies in northwestern Georgia where we have some foothills. But as you move to south through the state, you kind of lose a lot of that. So as far as I know, there's no plans to expand right now. But who knows? I'm definitely not on that side of it.
Yeah. What about the presence of renewable energy there? You have a lot of PV and probably no wind, probably, right?
Yeah, I don't think we have a ton of wind. They're definitely pushing more PV though. I'd have to look back on how much, what percentage of our overall portfolio, or whatever they want to call it, is moving to renewables. I know there have been significant gains in the last few years, and I think it's primarily centered on PV. Yeah, I don't think wind is a big piece of it.
Do you have any ideas about, what is the capacity that you have, capacity of generations you have now?
Off the top of my head, I couldn't say. I should probably know that.
It's okay.
The site I work for is 1,200 megawatts, and we've got 12 sites, but I think we're the largest. So
yeah. So what about nuclear? You have a nuclear power plant or not?
We do. We don't operate them, but we're like, I was amazed at how complicated the ownership of generation is. We have stakes in Vogtle, so we're part owners of that, but those are run by Georgia Power and Southern.
So your company is kind of co-op, right? Or is that? So you have memberships, or is that like a single company? So
it's we call it the family of companies. Back in the 70s, it was called the Rural Electrification Act that in Georgia was a big push to get electric power out to rural locations. As a result, Oglethorpe Power was formed to provide electricity or electricity to these rural electric member co-ops that popped up in these locations. Eventually it split, so Oglethorpe only handles generation, and the family of companies encompasses Georgia Transmission Company, which is the transmission arm from generation to the EMCs, and then GSOC, which is the controller. But yeah, we're a not-for-profit utility providing power to member co-ops.
Okay, thank you, Brandon. So I'll move to Alex now, the second presenter. Let me make you a co-host. So go ahead, Alex.
Okay, so my name is Alex Rhodes, and I am the graduate student that has been working with Thomas Brunner, Trey Davis, and Dylan D. And our project is about a mobile renewable electric power plant. I wanted to lean on my background a little bit of integrating different systems into one unit. And so I thought, what better way to do that than to try and integrate the different renewables that we are learning about. Okay, come on. So the concept is to provide a renewable power generation system to campers for off-grid camping. But then as I was working on this and thinking about this more, it became clear that this could also be utilized for a light duty power generation for disaster relief, as opposed to trying to source diesel or gasoline in those disaster stricken areas. We could pull this system in and do it passively. So this particular system that we're looking at is designed to provide an output of 2,800 watts at 120 volts AC. The storage is expandable. It's designed to start at 10.32 kilowatt hours, but that is, like I said, easily expandable by putting additional batteries in parallel, as long as you're running on the, as long as the batteries run on the same 12 volt bus that the system's designed for. And there's also other buses you can use, but we'll get to that later. If all three power generation types are running at max output, the generation is a little bit over 1 kilowatt, which is not terrible. And the unit is also capable of plugging into the grid at a remote locate or at any location for faster battery charging if you haven't used it in a while and you need to haul it somewhere. You can plug it in and charge batteries. So our first little thing is our photovoltaic generation. It's approximately 400 watts. And for ease of use for all of these components that we're using, I wanted it to be something that an average Joe could buy. So all of these you can find commercially, either off of Amazon or direct from the supplier. So this is the solar kit that we found. Now this was specifically built for like RVs. However, you can easily plug it into the system as a whole, as we are. So this one includes 4 100-watt solar panels measuring 42 by 19 by 1.3 inches in dimensions. It comes with a controller, cable tray. It comes with basically everything you need to mount it and hook it up to your batteries. Again, this is if you just want strictly solar. Collectively, all of them output 400 watts. This one has a pulse width modulating charging controller and is specifically designed for RV applications. and it comes with an LCD screen to display system operation information. The panels themselves is, if you were to lay them end to end, is 3.5 by 1.6 per panel. So you can get away with an area of 3.5 by like 6.5 feet. So they're very space efficient for 400 watts. And their efficiency rate is relatively okay. After 5 years, you're sitting at 95, 10 years, you're at 90, and at 25, you're at 80%. So your degradation is acceptable, I would say. And then we also wanted to include in current energy conversion, or generation. And with this one, we found a little generator that can provide approximately 350 watts. It's a little generator hooked up to a paddle wheel, basically. It's under $200, and it allows for over 90% generation. And this is great if you're like in a mountainous area, or if you have a river or a supply to water that can run with a reasonable amount of pressure. There is a downside. They require enough pressure to get rated power output. So you can get, you need a high head change to get the pressure to spin it. However, the wheels are efficient under low RPMs. Again, so you can get that pressure either by larger head or more pressure through, well, just like hooking up to it a hose spigot or whatnot. And then the last one we are using is wind generation. And this one also provides about 400 watts of generation. It's kind of hard to see now that I'm looking at it on the screen, but it's a little 400 watt 3-blade generator. It runs on either 12 volt or 24 volt. So you got a little bit of wiggle room there for your system. Your rated voltage is 27 to 54 volt output, and your battery voltage is 12 volt, which fits perfectly for our system that we've designed. And it's a 3-blade system, and it has a little tail on it so it could swivel and make that way you don't have to automatically rotate your generator to maximize your power output. And it only retails for $140. You can use them on, they're commonly used on boats, gazebos, remote homes, and mobile homes. And the startup wind speed is relatively small, only 2.5 meters a second, or 8 feet per second. It's not bad. And your rated wind speed is up to 12 meters a second. Now, all that generation is great, but it's worthless unless you can store it. Now, there are many different types of storage out there, including lead acid, flooded lead acid, sealed lead acid, and then you got your lithium ion. However, your lithium ion is more expensive, but it has more kilowatt hours capacity per pound. For this project, we went with this 800 amp hour at 12 volt DC, which equates to your 10.32 kilowatt hours capacity. It comes with all the cables and batteries. They're the cheapest to buy, and you can buy them they're in ranges of voltage 12, 24, 48. And you can combine batteries of the same voltage levels to expand your capacity. However, the flooded lead acid batteries weigh a ton. These 4 batteries alone, according to the specs, weigh approximately 600 pounds. So if you're putting it on a mobile unit, as we are, weight is a serious concern. However, if you have the money to blow, you can buy your lithium batteries to get more capacity. And again, it is expandable as you put batteries into parallel. If you find your base of 10 kilowatt hours is insufficient. Now we have a charge control and inverter system here. This one's designed for 2.8 kilowatts, and it comes with breakers on the front, so you can breaker your inputs and your outputs, which is awesome for isolation purposes. And also this guy has a breaker for your line input to charge your batteries remote or from the grid. But the system, there's a system monitor on it that gives instant status and percent full battery info. That way you can quickly see how full your batteries are. There's additional breaker spaces in there if you want to add more. Inverter bypass switch allows your choice of generator or grid or inverter output. If you want only generator output going, it's very flexible. It's easy to connect color-coded bus on the inside, and for AC and DC connections, it has multiple available knockouts for conduit. It has a single system grounding point, and it's got your clearly labeled connection points for AC and DC input and output to make connections to your generators and your AC output, whether that be on an SO cord or just a standard receptacle. Now, all of this together would be kind of a jumble of mess, so why not throw it into a closed trailer? Something like this trailer itself here is a it's a 6x8 trailer, closed trailer, and it's a place to keep batteries and other electronics shielded from the elements, unless you're can find some of those items that are NEMA 4 rated. And you can output the power via an SO cable terminated with plugs or via GFCI outlets located on the exterior of your trailer. You can store all of your panels, your generators, all the poles for your wind turbine, all inside. So it's all handy in a little trailer, and it's pretty fantastic. And these are the references for where we got everything. Again, you can see these are very commercially available. And so it's now, in terms of cost wise, it is extremely cheaper and more cost efficient to go with a diesel or a gas generator system, or a propane generator. However, if you don't have access to those, this is a really nice passive way to generate electricity for your off-grid needs. Are there any questions?
Any question, guys? Any question for Alex?
Did you consider, because like if you use lead acid batteries, isn't that going to outgas hydrogen? Did you consider venting on that?
I did not consider venting, but you are correct. They do outgas. Where it's a trailer, I guess trailers aren't the most airtight, but it is possible. You can always punch vents in a trailer. It's not I didn't think about that, but that is a good point.
Okay, no worries. Thanks.
Anybody else?
But like I did mention, they have the sealed lead acid batteries available as well for storage. So that would eliminate your outgassing problem.
Anybody else? So, this is very interesting, and you even know the prices, and looks like your student interns are also excited about this. And thank you very much. I will pass on to Kyriakos. Find you here. I will make you co-host. Go ahead.
Okay, can you see my screen?
Yeah, not yet. Yeah, okay.
Okay. All right. This My name is Kyriakos Varghese. I'm the grad student, and Tyler Sneed and Kyle Stewart were the undergrad students that helped me on this project. This is titled Benefits of a Microgrid. The background is that the existing power grid is increasingly challenged to provide clean energy with low carbon emissions. Reliability of the grid is in question due to aging infrastructure and seeming inability to meet loads during periods of high demand or extreme weather. In the case of Texas, about 2 months ago, many places also suffer from a defective or a non-existent power grid. One solution for this is the microgrid. A microgrid is a local energy distribution network. It relies on local means of energy production and typically consists of loads, renewable energy sources, energy storage system, and a connection to the power grid or a macro grid if available. The microgrid is capable of operating in either island mode, where it functions autonomously, or in grid connected mode, where it is connected to the grid. This is a little diagram or example of a microgrid. You see the distributed wind and solar, energy storage, loads, microgrid controller, and the connection to the grid. So microgrids can be categorized into either grid connected microgrids where there's connection to the power grid, or into remote microgrids where there is no connection to the grid because there's no transmission and distribution infrastructure. Microgrids can also be categorized into, it can be categorized depending on who the owner is or the use is, such as military microgrids, utility, campus, commercial, and community microgrids. This presentation looks at the benefits of a college campus microgrid. So we obtained load data from a university in Alabama. There's about 18,000 students. This is the load profile. The peaks are in July to September, and then the valleys are in January and February. The total annual load is 108, about 108 megawatt hours. So for the PV system, so for a renewable energy source, we used a solar PV system. It can be designed to meet the needs of a microgrid. NREL has an online solar calculator called PV Watts. The inputs are shown here. We'll use the location for Auburn. DC system size is 100 kilowatts, and the remaining inputs are mostly standard. Okay, this is the output of that calculator. The solar radiation is for the month, it's the average for the month, the monthly energy production, and then the dollar value was based on the input of 11.7 cents per kilowatt hour. For the PV system calculations, using that annual production of 141,655 kilowatt hours, 100 kilowatt system size, 5.39 hours per day, and then 365 days. It's a 0.72 D rate. And then we used the standard 16% efficiency for a polycrystalline solar panel. And then the area required was 625 square meters. And then on a college campus, this required area can be met with available space on campus building rooftops, or even an open field. So a battery system is needed to cope with the intermittent nature of a PV system and to also supply power to the microgrid when there is no power available from the power grid. So we use the largest monthly load from September. That was 11,420 kilowatt hours, and divided by 30. The daily load is approximately 380 kilowatt hours, assuming a need of 36 hours of capacity, 1.5 days. So we assume that the battery storage minimum capacity is 570 kilowatt hours. There are several off-the-shelf battery storage systems on the market. We looked at the Tesla PowerPack. Each PowerPack is sized at 232 kilowatt hours. And then using 3 of them results in a total capacity of 696 kilowatt hours. So that would provide power for just over 36 hours. It's just a picture of the Tesla PowerPack. So the PV system alone is able to meet the energy demands of the campus. We see the figure here, load versus PV generation, the monthly load in blue, and then the PV generation in green. Except for September, which had the highest monthly load, there was a bit of margin each month. This is the table of the excess energy each month. I realized I forgot the column here on the left for the month. But energy can be sold back to the utility from the microgrid under net metering or feed-in tariff, or a power purchase agreement if it's in place. Now, Alabama is one of the, I think, 3 states that does not have net metering systems in place. We didn't do a specific cost for the microgrid, but we looked at just the general economics. Each installation is unique, and so it can be challenging to generalize costs. NREL performed a microgrid cost study where they collected data from various microgrids in the United States. The study found that the mean cost estimate for campuses was approximately $3.3 million per megawatt. And then the percentage of the cost by component is shown. So the conventional generation was 76% of the cost, renewable 10%, energy storage 9%, controls 3%, soft costs 2%. And then additional infrastructure was, if needed, was less than 1%. The study also noted that often microgrid projects are built in phases, and they usually leverage existing infrastructure and distributed energy resources from previous projects. So looking at the benefits of a microgrid for the end user, the benefits include increased energy reliability with battery storage providing energy as needed, reduced energy costs, and it's also a source of energy if it's a remote region without an existing grid. There are also benefits to utilities and the government. Transmission and distribution system upgrades can be avoided or deferred. Transmission losses are avoided. Reduced emissions, and then government incentives can be available for renewables investments. Looking at the future of the microgrid, in 2016, the US had about 1.6 gigawatt of installed microgrid capacity. That number was expected to increase to 4.5 gigawatt by 2021. In 2019 alone, there were 546 microgrids installed. Most were under 5 megawatts. The Santa Barbara School District has a proposal and is moving forward with 6 solar microgrids, totaling 5 megawatt of solar and 5 megawatt of battery storage. And then standardization and declining costs of energy resources will reduce development costs. For the references we used. And any questions?
Any question, guys?
Did you consider adding any other distributed energy resources to this grid besides just the solar generation, such as maybe existing diesel gens or wind or anything like that?
No, we didn't. For a college campus, it might be a little bit challenging to add wind just because of the effects of the wind turbines on campus. But to answer your question, no.
Any other questions, guys? So I have questions for you. You work for a consulting company, right? Did you work on this or not?
No.
No?
I work for a nuclear power plant, so
Oh, okay.
so I just work solely in engineering at the plant, so we don't really get involved with any of the other generation that our parent company gets involved with.
Oh, I see. Okay. Okay. It's very good. Yeah. So what do you get help from your students, right? For student interns, looks like they learn something, you know, for example, from Alabama, you got some data. How do you get the data? You know, this is from one of the Alabama colleges, right?
Yes, we received it from a university in Alabama, and it was sent to us from someone that works there.
Oh, I see. Okay.
Yeah, the university doesn't publicly release that information, so that's why we didn't include the name of the school.
Okay, I see.
But
All
we
right.
just used that low data as a baseline.
Yeah, yeah. But it looks like you are a little bit over designed, right? You're basically selling electricity most of the time. I'm not sure if, you know, because your data doesn't include like in you know, short time period, you know, there could be some time where you actually your load is like higher than your productions. Definitely at night you don't have anything there, right? So the way you present your graph, you're looking at like really average data.
Right.
It's not instantaneously. Okay.
Correct.
Okay.
Yeah, this is the long-term monthly.
Yeah.
average.
Yeah. It's very interesting. So this is a microgrid concept, definitely the way for the future. It's getting cheaper, and there are a lot of standards being developed now, and you know that should help. Well, is there any questions for all the presenters today? Any question at all from all of you? So if not, then we are going to close for these presentations. And thank you very much. Bye-bye now.